we make strong basic with the lithium hydroxide until pH 13. Again, high temperature for 30 minutes. Again, water, vacuum distillation at almost room temperature. And we take off always the top and the bottom of the distillate, so usual procedure. And we stop when the pH solution is about 8 and stable. And the resistance, as seen measurement, is larger than 400 kilo per centimeter. Moreover, we have to develop a new circuitry to strongly reduce the deloading after reaching high values of deuterium over palladium. So there are several problems altogether, not only one. Moreover, we add some silica, very, very thin silica, 12 nanometer diameter, with some proper very poisoning bactericida, in order to reduce the force growing of bacteria after purification. And we add mercury only when the loading is enough large, 0.9. So this is the new circuitry that we develop in order to avoid long time the loading of the system. It's similar to previous one, with the addition of a relay and some electromigration, and with the constant current diode, and we use a side effect of relay in order to get for 2 milliseconds like pulsed condition where the current flowing in the wire change from 5 milliampere up to sometimes 3 ampere, and the DC current change from 50 milliampere up to 100. Okay. Okay, this is some formula about this circuitry. And the repetition rate is every 100 seconds. Okay, using this kind of pure water, purified water, and this circuitry, we get a quite strange behavior. This one, the resistance ratio was low as 1.59, so lower from the Cooper limit, so good point. And moreover, when we decrease the current from large value, but for us large is just 40 milliampere to half 20 milliampere, instead of the loading, so means resistance has to increase again, there is still loading, but this is not true loading. It's just a strong indication that we have a chest heat in this region. We decrease current, the chest heat almost disappear, and after is a conventional deloading. This experiment was reproducible. We tried 3 times. When you get very large loading and make this procedure, always you get this value. The amount in this region is of chest heat, alcohol chest heat, is about half watt over less than 2 watt of input power. More other data, but I skip. One similar result was obtained at Pirelli, but I think Dr. Gasarbelli will speak to you more detail that I can. Here is a short table of the system without using the new circuitry, but just using very kind of purified water from my friend Antonio Spallone. About bacteria, I want to say that the people know that they can grow in heavy water, but I think in our community nobody know before. One key point of bacteria that when you add some new bacteria in heavy water, there is some time to adapt, and after can grow but at a reduced rate in a weaker condition. This for almost any kind of bacteria that can survive in heavy water. The bacteria closest to our, but not the same, is Rastonia pichetsi. It's family of Pseudomonas and it's very thin bacteria. It can pass 0.2 microgram filter. The behavior is similar to another kind of Rastonia, Eutropha, that eat mercury, lead, nickel, chromium, in our experiment. So it seems between Rastonia eutropha and Rastonia pichetsi. This curve shows how our bacteria can grow in light water and heavy water without adaptation. This is the first bacteria reported in the biological literature that is indifferent to stay in light water or heavy water. The first one. Yeah, okay, sure. How to select, believe to biologists is here, so you can look after everything. The difference with most close is only 0.13%, but enough to say it's a new bacteria. Picture bacteria. You can see. But even it's large, but it can pass through small diameter filter because they don't have envelope, so they can flow, pass through. Here in a polluted way. Small proof that there is a new bacteria. Okay, they can survive in strontium chloride very well. And in mercury. This amount is lethal for the human. Don't forget. Bacteria. And this is another proof that it's not a conventional bacteria because the Rastonia pichetsi is a sensitivity or resistance. We have two not matching for tetracycline and streptomycin. Different matching. Conclusion? So we think about light water, the problem is solved. Our experiment was produced at the Pirelli in Italy and the Stanford Institute, Mallove in the United States. We have problems with the same procedure used for heavy water don't works. We have some that with the proper purified water, the proper circuitry, the strong indication of some HSE reproducible and controllable. But the problem is that the HSE in only some spots. In our experiment, we inspected 50 centimeters. We found only 2 spots where the temperature is anomalous, and the length only 4 millimeters. So still localized, not all the while. So we need more work about purification. But I want to say this point. The bacteria identified is previously new, but because of this, we can help the environment polluted because this bacteria eat mercury and lead. So it is a present due to cold fusion studies, present to you, all to you. Thank you.
We have 2 minutes. Please.
I have only one suggestion. Why don't you use ultraviolet light to kill the bacteria and remove them instead of heating and all that? They're more efficient. Ultraviolet light, UV, ultraviolet radiation.
UV.
Yes, we try. Okay.
So question is, are you trying to use UV light to kill the bacteria?
Okay. Now there is.
Turn it on.
Now there is experiments made at Cascasaccia to use a very large amount of radiation to kill bacteria, but it seems ultraviolet not enough effective. Anyway, the problem is that you have to put ultraviolet inside the cell calibration zone. It's better to take off before for practical aspects.
You mentioned you had the 4 millimeter long active spots. How did you know that was active?
Yes.
Got a very quick question.
We use they call infrared gun, so you can inspect the wire, infrared gun moving, and we have found in some small area of the wire an increase of the temperature in respect of the water before or of the wire of about 1.1 centimeter in one spot, and the other 0.7 degree. So this is not. It's really unexpected. So there are some odd spots.
I just had a very quick question. You had something from a paper where written on the top you showed the website. The website, the HTTP. Could you put that back up? So I can
Later, yes.
all right. Well, okay.
No more questions? Just a short question.
Really cool.
So the question is, have you used some model microorganism, another one, that only this one? Because it's possible to modulate biodegradation. It's very big literature about it.
Okay. We know there is at least this bacteria, but we have indication that there are other bacteria. But now we focused on this one because it seems the most likely to give problem to us. And perhaps even some small views or so on. But we need time to work. So it's just starting point. There is bacteria in daily water, we have to take off or study deeply to understand why it works or don't work. Just starting point.
Thanks to our speaker again. Next speaker is Dr. Iwamura. Talk about nuclear products and their time dependence induced by continuous diffusion of deuterium through multi-layer palladium containing low work function material.
I'd like to talk about nuclear products and their time dependence induced by continuous diffusion of deuterium through multi-layer palladium containing low work function material. Here is an outline of my study. I will talk about, at first, the background and features. Our study is characterized by multi-layer palladium and continuous diffusion of deuterium. Next, I will talk about experimental results and discussion. We perform 2 kinds of experimental methods. One is a D2 gas diffusion method, and the other is an electrolysis diffusion method. D2 gas diffusion method, which can analyze the element on the palladium sample by XPS, X-ray photoelectron spectrometry, without taking the sample out of the vacuum chamber. It is also possible to analyze time dependence of nuclear products. And carbon to magnesium to sulfur or silicon, the transmutation process was observed by this method. Next experimental method is an electrolysis diffusion method presented at ICCF-8. By this method, larger reaction rate and excess heat analysis are possible. We obtain silicon powder nuclear products with anomalous isotopic composition. This is a hypothesis of our study. We examine palladium cathodes by EPML or XPS, and we conjectured that certain impurities play an essential role to cause nuclear reaction. So we assume that necessary conditions to induce nuclear reaction in solids are existence of a third element except palladium and deuterium, and 2, enough diffusion flux of deuterium, and 3, high D by PD. At present, we suppose low work function material is a candidate of the third element. This transparency shows the first feature of our method. We developed multilayer palladium which contains low work function material. It is composed of palladium seed and calcium oxide or Y2O3 or TiC, they are low work function material, and palladium thin film. You can see by this transparency, Cl and Y2O3 and TiC, the work function of them are lower than palladium. Next, the features of our method. The next feature of our method is a continuous diffusion of deuterium. This is palladium seed, which contains low work function material. On the upper side, deuterium atoms are electrochemically loaded or loaded D2 gas pressure. On the vacuum side, lower side, we keep a vacuum condition. So we have a continuous flow of deuterium atoms like this, from upper side to lower side. With this configuration, we can provide enough diffusion of flux of deuterium. And here is a chart that explains how to make a multilayer palladium. First, we wash palladium seed with acetone and anneal it at 9 degrees centigrade for 10 hours under vacuum condition. The sample is cooled down to room temperature and washed with aqua regia for 100 seconds to remove impurities on the surface of palladium. At that time, the sample is covered with a complex layer. It is formed by simultaneously sputtering of Cl or Y2O3 or TiC and palladium. Thickness of the layer is set 1,000 angstrom or 3,000 angstrom. A thin palladium layer, 400 angstrom, is made on it by ion beam sputtering. The complex layer is put up near the surface because we consider that nuclear reaction occur at the surface, at the near surface of the palladium. Let us move on to the next point. This figure shows a cross-sectional view of the D2 gas diffusion method. And this is a palladium multilayer palladium. Okay? And this blue part means the D2 gas. D2 gas is fulfilled at one atom. This chamber is evacuated by turbomolecular pump. So we have, this chamber is evacuated by turbomolecular pump. So we have a deuterium flow through the multi-layer palladium. X-ray photoelectron spectrometry is available in this chamber. XPS is composed of two parts: X-ray GAN and X-ray GAN for excitation, and photoelectron energy analyzer. This figure shows enlargement of multi-layer palladium. D2 gas upper side, D2 gas and vacuum side. D2 gas and vacuum is divided by this multi-layer palladium and this gasket. Upper side, the multi-layer palladium is the film side, thin film side is the upper side. This is the top view of the multi-layer palladium. D2 gas passes through this red region. Next, we explain the procedure of the D2 gas diffusion method. And this graph is a typical example, time dependence of element A and element B detected by XPS. And this shows the change of D2 gas pressure in this region. And at the lower side, procedure of experimental procedure are written. At first, we make the multi-layer palladium, and the sample is set in the chamber and heated up to 70 degrees centigrade. Then the chamber is evacuated. So, evacuated after we obtain enough D2 pressure, about 10 to minus 8 torr, to confirm, to perform XPS analysis. We analyze the surface of the sample to confirm that other elements do not exist except palladium and carbon and or the elements we add. Small amount of carbon is difficult to remove in this kind of experiment. So usually we detect carbon at this moment. Okay. During this period, nuclear reactions occur. After a certain period, the D2 side chamber is evacuated to 8 to minus 8 torr. The surface of the multi-layer palladium analyzed by XPS. Typically, we detect new element like B that did not exist before D2 diffusion. So, after XPS analysis, the chamber is fulfilled with D2 gas again. The second time, D2 diffusion starts. After a certain period, D2 gas is evacuated. Then we perform XPS analysis again. Typically, we observe change of the element of A or B. In this way, we can obtain time dependence of nuclear products. And the important point is that the multi-layer palladium sample is not taken out of the vacuum chamber. So there is no contamination effect from outside of the chamber. This is a photograph of D2 gas diffusion apparatus. Main chamber is here. And X-ray gun for XPS, photoelectron energy analyzer, And this is a germanium detector. But we have never observed X-ray or gamma ray change during D2 gas diffusion. XPS is a method of identifying elements by the energy analysis of photoelectron, which is induced by X-ray irradiation, like this. Some assumptions of XPS analysis are given. Both the intensity of X-ray and the irradiated region are constant. The depth of analysis is set at 20 angstrom. And third, atomic number of the detected element is calculated by both palladium peak intensity and ionization cross-section of the element. So next I will present our experimental results on D2 gas diffusion method. We perform three types of mass experiment. One is a palladium only. Second, the palladium calcium oxide palladium. And third, a palladium with lithium and calcium oxide palladium. Lithium is introduced on the surface by electrolysis. Okay? The first sample is palladium only, which does not belongs to multilayer palladium. Upper figure is XPS spectra at T equals 0, T equals 46 hour, T equals 91 hour. These peaks are attributed to carbon and photoelectron. We can see that there is almost no difference between T equals 0, 46, and 91. Lower figure shows the time dependence of the carbon, impurity carbon. Carbon is constant, as you can see. These figures show time dependence of impurity carbon on magnesium and sulfur and silicon on the multilayer palladium. And the multilayer palladium is composed of palladium and calcium oxide and palladium. And we performed two times this type of experiment. Okay. At T equals 0, no element except carbon can be found, of course. So, but after 42 hours, we obtain magnesium, sulfur, and silicon XPS peaks. On the contrary, carbon peak was reduced. At the time equal to 116 hours here, sulfur and silicon increased and magnesium decreased slightly. Carbon decreased. Silicon and sulfur is increased monotonously. And magnesium once increased and decreased. Next, number 3 experiment. In this case, carbon is slightly larger than number 2. After 24 hours of D2 gas diffusion, we detected magnesium and sulfur and silicon again. And after that, as you can see, magnesium is decreased and sulfur and silicon is increased monotonously. So we have good reproducibility on this experiment. According to the experimental results, we may consider that carbon is transmuted to magnesium, and magnesium is transmuted to sulfur or silicon by certain nuclear reactions induced by our experimental method. These are the XPS spectra on carbon and magnesium at T equals 0. Carbon peak is here. And gradually, at T equals 0, carbon peak is high, but gradually, the height of the peak is decreased. And this is XPS spectra of magnesium. At T equals 0, there's no peak of magnesium. But T equals 76 hours, we can see the magnesium peak clearly. And then T equals 116 hours, the peak of magnesium vanishes. Here are the XPS spectra on silicon and sulfur and palladium. As you can see, there are no peaks on silicon sulfur at time T equals 0, but after that, we can see the peaks. And the lower figure shows the spectra of palladium. Palladium spectra are constant. In addition to XPS analysis, we performed SIMS, secondary ion mass spectrometer analysis of these samples after experiment. And this figure shows a comparison between palladium calcium oxide and palladium only on isotopic abundance of sulfur. Upper figure shows secondary ion mass intensity of number 1 and number 3. Number 1 is a blue line, palladium only, and the red line is material cathode. And the lower figure shows the isotopic ratio by sulfur 33 by sulfur 32, sulfur 34 by sulfur 32. As you can see, sulfur 33 by 32 is of number 3 is enormously large. On the contrary, the other value correspond equal to natural abundance. Green line means natural abundance. We observed that carbon was transmuted to magnesium, sulfur, and silicon. Then we add lithium on the palladium surface, aiming that lithium will be transmuted into another element. These are the results of lithium-added multilayer palladium experiments. Lithium might be transmuted into fluorine and aluminum. In the case of number 4, fluorine increased once and decreased, red line. Aluminum emerged at the end of the experiment. Magnesium once increased and decreased in the same way of the palladium calcium oxide experiment. In the case of sample number 5, we also similar time dependence of fluorine and alumina and magnesium and silicon. Fluorine up and down, aluminum up, magnesium up and down, and silicon increase monotonously. At present, we assume that fluorine and aluminum are transmuted from added lithium. These are XPS spectral lithium doped multi-layer palladium. At T equals 0, there's no peak of fluorine. But however, T equal 74, we can see clear peak fluorine and magnesium. And there are also XPS spectra of sample number 5. We can see aluminum peak and silicon peak. This figure shows a comparison between lithium doped multi-layer palladium and palladium only on fluorine and aluminum by SIMS. Blue line is palladium only, and green and red line attribute to lithium, palladium, calcium oxide sample. So we can see fluorine and aluminum detected by XPS are also observed by SIMS. Now, let's go on to the discussion of the results of D2 diffusion method. Number 1, time dependence. Magnesium and fluorine up and down. So we have a natural question. Can impurities behave like this? I think it is very difficult to explain this time dependence by contamination. Number 2, anomalous isotopic abundance. We obtain sulfur 33 by sulfur 32 equal 0.25. Such efficient isotope separation is possible by impurity. And number 3, method of measurement. We perform XPS analysis without taking the sample out of the vacuum chamber. So we think it is strongly suggested that magnesium and fluorine and sulfur are formed by certain nuclear reactions. Let's move on to the next point. This figure shows cross-sectional view of the experimental apparatus of electrolysis diffusion method. An electrolyte of lithium oxide and D2O and the vacuum chamber is divided by palladium, multi-layer palladium. Deuterium atoms through this like this. And the cell of the electrolyte side is made of Teflon and polypropylene, which have resistance to lithium OD solution. And the cooling pipe is made of nickel, which is also resistant to lithium OD. This is a photo of electrolysis diffusion apparatus. We can see cell and chemistry detector and vacuum chamber. These photos show the difference between before and after electrolysis in the case of no powder product. Before electrolysis, multi-layer palladium is like this, and after that, like this. But on the contrary, we cannot see any products inside of the cell. However, sometimes we obtain the products like powder. So the change of the inside cell, you can see. So I will show you the experimental results on electrolysis diffusion method. One, Fe isotope ratio anomaly. This was confirmed by SIMS and time-of-flight SIMS analysis. And 2, silicon powder nuclear products. We perform many experiments with this type of cathode. So even 75 is produce excess heat and X-ray and nuclear products, and isotopic ratio is different from natural abundance. So I will examine, I will explain this sample. This is a SIMS analysis of EV75. We can see the 56 and 57 peaks here. So iron 57 by iron 56 is enormously large, as you can see. This is top SIMS analysis, time of flight analysis of EV75. With this time of flight SIMS, we have a good resolution. So we can identify iron 56 and iron 57. So we can see iron 57 by iron 56 is larger than natural abundance. So enormous large Fe57, Fe56 is confirmed by both SIMS and time of flight SIMS. And we have short time, so I will show you the detected silicon powder product. This photo shows a silicon powder product. It is a SiO2, and estimated mass of silicon is 0.057. We examine the candidate of the silicon impurity and estimate like this. So we see that detected silicon powder is larger than total silicon impurity. And furthermore, this silicon powder, the isotopic ratio of this silicon powder is listed in this table. These are the silicon standard solution. We can see isotopic abundance of detected silicon powder is different from natural abundance. So at present, we think that detected silicon powder is composed of nuclear products and silicon impurity. So now concluding remarks. Two kinds of experimental methods have been developed to induce nuclear reactions. One is the D2 gas diffusion method, and the other, electrolysis diffusion method. Common feature of the method is to cause continuous diffusion of deuterium through a multilayer palladium and that contains low work function material. Time dependence of nuclear products, magnesium, silicon, sulfur, and fluorine, and aluminum were observed by the D2 gas diffusion method. The results were reproduced qualitatively. Sulfur 33 by 32 of the product is one order larger than that of natural abundance. Iron isotope ratio anomaly of the multilayer palladium obtained by the electrolysis diffusion method were confirmed by SIMS and top SIMS. Isotopic composition of silicon powder products was anomalous. Thank you for your attention.
We have 4 minutes, please.
Okay.
Have you tried with hydrogen?
Hydrogen? Only with multilayer palladium, only 2 or 3 times I performed the experiment. But we cannot find any signature of nuclear products.
Are you trying to do more with hydrogen, see whether you will produce similar thing or not?
I think it is interesting to perform by hydrogen isotope. But now we are doing experiment by deuterium only.
In the deuterium experiments, is there any correlation between heat you observed and my cross?
Yes, that. Excess heat is observed in the case of deuterium experiment.
Well, I've seen that you made micrograms of the excess elements. Well, very easy, you can make grams with more easy methods. I've listened some of them years ago in my previous papers in ICCF. You can pass directly to grams instead of micrograms.
You say the
If you want to make silicon, for example, you can make carbon plus oxygen and electric fluid. You can make a lot of silicon.
easily can be made.
Yeah, you
Gram
can make
or
grams.
grams.
No, it's not micrograms.
Have you observed any changes in the palladium isotope ratios?
Usually, we cannot see any difference of palladium isotope because I think palladium is number of the palladium atoms is very large. So if change, we cannot detect. I think.
Quick question. You mentioned 1.4 watts excess power. Can you tell me please how did you calibrate the experiment for the gas experiment?
Gas experiment?
like-
Gas experiment?
Yeah, how did you calibrate the cell?
No.
So the-
We didn't measure the excess heat of gas experiment. We measure only electrolyte experiment.
Okay, and another question please. The accuracy of XPS is quite bad for light elements like carbon. You haven't plotted the error bars on those plots. Is the variation of the concentration considerably larger than the error bars for those data points?
Okay. It is difficult to detect the carbon by XPS, you say?
I think so.
We specified by the other P. Okay? So we think it is a carbon, attribute to the carbon.
Did you use a single batch of palladium, or did you use multiple batches of palladium?
Pardon?
Was your palladium, the
Yes.
source of palladium, was it all the same kind of palladium,
yes,
or
yes.
was it?
All the same from Tanaka Kizo.
Did you examine the surfaces, and I mean, could it be that
Oh.
some of the impurities might have come out of the surface after prolonged exposure to deuterium?
Yeah, we examined
You did.
on the surface,
You did.
and some
There was some there, but it was very
curious,
different.
phenomena happened on the surface.
I see.
But I cannot tell about.
I was thinking of prior to the experiment, prior to putting it in, you know, looking and seeing what the things look like. Well, anyhow.
You're very sharp to me.
In the nuclear transmutation, several experiments shows localization of the products. Did you make such a experiment to confirm the localization?
Okay, localization. We observe sometimes the localization of nuclear product. It's an example of the. We can see the color of the region is different from here and here, and usually the other elements detected. So yes, we see the localization of nuclear products.
Thanks to our speaker again.
Thank you very much.
paper is UFR, hydrex catalyzed transmutation of uranium into lead.
I'm going to report the results of a number of experiments we did on the system uranium hydrogen. And when I say hydrogen, it's light hydrogen. I will describe rapidly the excitation means that we used and give you the main experimental results, which are the following. We have observed up to 1 watt with an uncertainty of plus or minus % of excess power or energy, and the apparition in the samples of lead and of one specific lanthanide, which is lutetium. We have also observed modification of the isotopic composition of the uranium and of the alpha, beta, and gamma spectrum. Finally, we will give a quick interpretation of these results through the hydrex nucleus cluster concept, which we think can explain a number of results in the fields. The hydrogen uranium system we are using, we start in fact from very pure uranium of nuclear purity, which has been given to us by Kojima, and with this isotopic composition. You can see that we have characterized the uranium by its ratio 235 to 238, which is a very common measurement used by nuclear people. This is the uncertainty on this ratio. And the figure you see here is the ratios for terrestrial uranium. You can see the variability of our samples because we have used the same batch of uranium for the whole experiment, 150 grams, and we have analyzed more than 20 blank samples. So this is the uranium system we use. We use, of course, we are speaking of the hydrogen uranium system, so we are using uranium hydride. Uranium is very easy to hydrogenate. You can reach very easily UH3, 3 minutes at 210 and 20 bar of hydrogen. And we have studied 3 hydrogen uranium systems. One is solid metallic uranium as such, which always contains between 1,000 to 2,000 or 3,000 atomic ppm hydrogen, uranium hydride of various hydrogen content, and powdered metallic hydride obtained by deogenating uranium hydride up to 1,000 atomic ppm hydrogen. The excitation means we applied to this system were the following: electrical current in the form of either DC pulse current with 5 kilohertz frequency or high frequency AC current with frequency up to 20 megahertz. And a magnetic field of high intensity up to 1 Tesla generated by permanent magnets, and this field is applied in a direction parallel to the current direction. The temperature was varied from 40 to 250 degrees C. The calorimetric experiments are carried out in 2 different setups. For the experiment using 5 kilohertz, we use a setup which has been described, and I will not go into detail. It has been described and sent and accepted for publication by Physics Letter A. And for the high frequency 10 megahertz AC current, we use a slightly different system, taking into account the special features of the high frequency current. The chemical composition were assessed by the total sample was dissolved, and we are using
a low or medium resolution ICP-MS for all species from beryllium to uranium, and for lead isotopic ratios, and a thermal ionization mass spectrometer for the uranium isotopic composition. They were performed by, these measurements were performed by two different laboratories. One is the central laboratories of the CNRS, the Centre National de la Recherche Scientifique in Solèze, and that's for all the elements except uranium, and for the uranium, the measurements were performed by Cogema Laboratories in Pierre-Latte in France. The dissolution procedure has been described, so I don't want to get back to it. And the alpha, beta, and gamma counts for excitation were made using common usual detectors. So this is a summary of the main calorimetric result. You can see here the frequency, so you have 5 experiments with 5 and 4 with 9 megahertz, and this is 5 kilohertz. And you can see here the temperature range. You can note that the temperature range for megahertz experiments is lower than the range for lower frequency experiments. The duration was in the order of 100 to 1 million seconds. And the total energy ranges from 188 kilojoule to 2.7 kilojoules. And if you report this excess energy to the amount of uranium processed, you can see that you have, of course, megajoule per mole uranium, which means that this is probably not chemical. So, this is just a curve to give you an example of how the excess energy occurs. This is the excess energy as a function of days here, and you see that it starts from 0 and increases progressively up to a certain maximum, which in that case is 800 milliwatts. These are milliwatts. The same occurs for the megahertz experiment. So, in order to try to understand the origin of this excess of energy, first I will give you a brief effect of the operating condition of the experiment. The maximum excess power you can see range from 90 milliwatts to 1,500. This is the limit of detection of our method, which is not more precise like 50 milliwatts. And one thing interesting you can note, this is the intensity. You can see that the 5 kilohertz experiments have a lower milliwatt per ampere than the megahertz experiments, which are higher. And the activation energy is higher for the medium range frequency and lower for the high range frequency. We have no clear explanation for that, but we think it's related to the synthesis of this Hydrex compound that we are going to talk about. Now, to try to understand where this excess energy can arise from, we have to take into account the chemical results. So what we have found mainly in the treated samples, the blank samples contains something like 2 ppm lead and less than 2 micrograms per liter in the solution coming from the dissolution of lutetium. So what we have found is quantities of lead up to 5,000 ppm, which is much higher than the blank, the lead contained in the uranium. And we have found lutetium, which is not found in the blank, in ppm quantity, but which for the sensitivity of the ICP-MS are very significant. So if you can see that the sample treatment varies from 200 to 500 milligrams. The energy of reaction was calculated previously. So these are the results in ppm of lead, and these are ppm of lutetium. So to try to understand what happens, you can divide by the number of the energy observed divided by the number of atoms of lead formed, and you can also divide it by the number of lutetium formed. And you have figures which are a bit puzzling. You get here reported, this is compared to lead, then you get, this is the order of alpha emission energy. This is surprising because it's very low. This is also, well, still in the range of alpha emission, and this is in the range of fission reaction, because this is in the range of 200 MeVs, because the immunity is kept here. And if you plot it against lutetium, then you get something which is extremely high for this experiment, and these two figures are in the range of fission reaction, which is 100 or 400, this is the range. The uncertainty on this figure is probably in the order of 100%, of course, due to the imprecision on the... But nevertheless, 100%, you can see that the different are interesting. So, I'm going to briefly comment on these chemical results. Well, for lead, as I told you, we have analyzed 20 blanks, and of course we have identified, we have in our, lead is very common, and we have identified in our experiments two possible sources of lead. One is the presence of tin solder in our experimental setup, by a complicated way, because you can have a migration of lead in the gaseous form, in the form of PbH4 coming to the uranium. Well, I'm skipping on that. And the second is the presence of 16 ppm of lead in the steel, which is used for the electrodes of our experiment. So I'm going to give a word about the lead. For the lead, we have done the isotopic composition of the product, and we have compared it to the sources of pollution in our experiments. And we have, first, I must say we have a reliable, very reliable analysis, because the two labs find exactly the same results. And what is interesting, I'm going around fast, but to understand what happens with lead, people generally plot the ratio 207 on 204 or 208 on 204 against 206 on 204. This is a usual way of doing when dealing with geochronology. And you obtain this type of curve. This is a curve for modern line, and this is the curve for 2 billion euros lead. And these are our experimental results, and these are the two possible sources of pollution. This experiment has been done excluding completely this one, so you can see that its isotopic composition is completely different from what of the possible isotopic composition of the source of pollution, and moreover, this one should have had an enormous content of lead, of iron, because this is the steel of the electrode. So what we say about that is that we cannot completely exclude, of course, that there has been a pollution, but what we are quite confident that we observe a mixture of real, genuine lead bioreaction and pollution lead. Then if we turn to the lutetium, then the lutetium is, as I told you, in the ppm range, but it's extremely significant because the detection limit is 2 micrograms, and we have observed up to 1,400 micrograms of lutetium in the solution. And moreover, there is a second thing which is extremely interesting. This lutetium has a very different isotopic composition, because we have a huge quantity at mass 176, which usually is only 2.5%. So this excess is either the signature of a modification of the isotopic composition of the lutetium, or a signature of the production of yttrium and hafnium, which are the two rare earth round lutetium. So we can say that unexplained lutetium has appeared in our samples. So I'm going to the conclusion because I still only have 2 or 3 minutes left. And to interpret these results, we consider what we call the hydrex nuclear concept, nuclear cluster concept. We suppose that a proton and an electron can build what we call an hydrex, which is a resonance, which is a metastable state, which requires energy to be formed, with a lifetime of 1 second, which is very long compared to nuclear time. And this production of hydrex could surround one big nucleus because they are of nuclear dimension, they are femtometals, compounds, so they can surround a nucleus to give something like a compound. You know, in nuclear reaction, you generally consider a compound nucleus, which is the result of the 2 nucleus coming one together. In that case, you have a standstill nucleus around which gather a number of hydrex, so you have something where many body nuclear reaction could happen without violating any laws, in fact. And just to make the drawing, and I will skip to the conclusion. So we imagine this nucleus like that, with a big nucleus like uranium or palladium or whatever you want, surrounded by these very specific hydrogen compounds here. And you could have a kind of nuclear rearrangement between what is inside that and what is here, because this is nuclear distance. And you end up with a kind of evaporation of small pieces, alpha particles mainly, and sometimes lithium, just due to a number of considerations in which I won't enter, and an evaporated nucleus of smaller atomic mass. And if you make some hypothesis on how this could work, then you should obtain from uranium, you should obtain mainly something from lead to lutetium as evaporated nucleus, and of course many alpha particles, as everybody finds. And in the case of palladium, you should find mainly zinc and copper with a number, of course, of helium-4. And I came back to an analysis we had 4 years ago when we were working on the palladium system. And in the palladium system, what we had found, and that's very interesting, we had found the apparition of unexplained excess of copper and zinc, and the apparition of some lithium, which in the case of palladium we think should happen for reasons which I haven't time to develop now. So my conclusion would be that we have now a measured excess of energy, we have now, I think, correctly measured production of byproducts, and we have a theory which we can discuss. So what we really think that the difficult step in all these things is the synthesis of the hydrex, of this intermediate, and we think that when we master this synthesis, then we can control what we would like to call nuclear catalysis. Thank you for your attention.
Very interesting talk, but we have 2 minutes left.
Hi. Have you measured gamma production, fast alphas, helium or helium-3 concentration buildup?
What is striking is on the gamma production, you can observe only small variation on during the experiment. And in fact, we have an explanation. In fact, we find that you have so many particles involved in the nucleus that most of the resulting products are likely to be in their ground state, in fact, stable products in their ground state, because it's a many-body problem. Sorry? Alpha particles is very difficult. We have an indication of production, but it is very, very difficult to measure because of the thickness of the sample. I can discuss that in detail with you. It's a problem, it's an experimental problem. But we have not measured helium production. We are going to.
Another question. How much uranium can you transmute in one day?
Sorry?
How much, with the quantity of uranium that you can transmute in one day?
The maximum we had was, in fact, production of 1 watt. So you can make the calculation.
You have no idea in weight how much uranium?
Oh, the range is in the range of 100 ppm on milligrams.
Ah, okay.
From your data, the formation of the hydroxide and thermic and few electron volts.
Right.
Then you can calculate the density of hydrox from the hydrogen atom density of the hydrogen.
Yes.
Then you can calculate how many emission or some nuclear reactions between hydrox and uranium or palladium.
Yeah.
Did you do that calculation? This is one question. And another one is, this is essentially the neutral particle.
Yes.
And in 5 femtometer near the nucleus, for instance, neutron interact with strong interaction. You wrote here electric dipole interaction. Did you compare the possibility of hydrox nuclear interaction and the neutron nuclear interaction? This is second.
You mean, well, the first question, your first question, in fact, we have no direct measurement of the hydrox products, so we can make any calculation you would like to do. It will be nonsense, in fact. The second is, if I understand correctly your question, you are telling how can the neutron can escape from the nucleus to combine. No, sorry.
For instance, background neutron we have and interact with the nucleus.
Oh, the background neutrons?
Yeah.
Oh yeah, it's much lower.
You propose the hydrox nuclear interaction. Which is stronger?
Oh, the hydrox interaction is much stronger than the neutron background.
How many hydrox?
Sorry, no, I didn't understand quite your question. It's in many order of magnitudes higher. It has nothing to do with the neutron background. It has nothing to do with the neutron background.
Remember the concentration. Hydrox concentration and the background neutron concentration.
Well, I don't know neither, so I can answer. No, what I know for sure is that the neutron concentration is extremely low. Right. Extraordinarily low. It's 1/1000th of count. We did measurement on the neutron background. It's 1/1000th, 1 on 1,000 count per second. So it's a concentration which is extremely small, extraordinarily small.
Next question.
Sorry.
In the case of palladium, you still have those samples which we could check the zinc isotopic ratio and the copper isotopic ratios.
Unfortunately, we of course have also dissolved them and send them to analysis. But maybe we can discuss the next experiment we do to send you a sample. I do appreciate that. Thank you.
This will be last question or comment. Your hydrox model nor any other model need to be worked out in detail before you can come up with predicted reaction rate.
Yeah, right.
So the comparing this with the neutron model won't do because there are lots of parameters, coupling constants, differences which has to be taken into account to come up with realistic predicted estimate.
Yeah, right.
So have you done that?
Now what I've done for tugging, I did the only thing we could do is to start from uranium or palladium, etc., and to see, you compute from the mass difference the energy released from uranium to lead, to lutetium, or for palladium to zinc, and you look how many hydroxide you need. And you arrive to something. We can discuss that. It's not, of course, very high-level quantum mechanics. It's only grocery, but grocery sometimes is efficient.
Thanks to our speaker again. Our next speaker is Dr. Warner. Effect of cold work on the amount of excess heat produced during the electrolysis of heavy water with titanium cathode.
Okay, in this talk, we're going to be focusing on mechanical treatment of titanium cathodes by cold rolling. Before we do that, though, I'm going to talk a little bit about the calorimetry systems we used. We had two that we were working with. The first one is an 8-cell experimental setup in which we had 3 pairs of 2 identical cells. We also had a control cell, which is a titanium or platinum cell, platinum cathode and platinum anode. And we had 1 cell dedicated to ambient temperature measurements. A typical cell for this 8-cell experiment is shown up here. And you can see that this is a pretty small cell by the scale here. We have an outer glass shell with an inner glass shell. This is dead airspace in here where we put a temperature sensor. Inside the inner tube here, we have just enough room for 3.5 grams of electrolyte, which is heavy water and sulfuric acid. And we have just enough room for about 3.5 grams of catalyst. Here we have a platinum lead, which is attached to a titanium cathode. And we have a platinum anode, which is also attached to a platinum lead. This thing, when it's completely set up, is actually pretty small, fits on a desk. Here are the cells themselves. These are all wired in series, so we can give each cell the same amount of current. These are power supplies. This is a circuit which we collect all the measurement leads, and we log them and collect them with the data acquisition program on the computer. Now, to analyze the 8-cell experiment, we've derived this equation here, where this term is the enthalpy released by cold fusion or some other unknown processes. This is the temperature difference between each cell and its surroundings. The subscript here denotes whether it's the experimental or control cells. The VI, that's the power input, voltage and current. This term here, this is the recombination enthalpy lost by the cell during the experimental run. This term down here is the enthalpy loss due to large difference between the enthalpy of formation of titanium deuteride and the enthalpy of recombination loss by the formation of titanium deuteride. I'm just going through these systems very quickly because we want to get to the results. The next system that we used is a Seebeck envelope calorimetry system by Thermonics Corporation of America. Now this allows us to scale up our experiment. You can see the scale here, the centimeters very much smaller than the previous. We can now use 75 grams of electrolyte, and we use about 20 grams of catalyst. We still have a titanium cathode attached to a platinum lead and a platinum anode attached to a platinum lead. The circuit for this experiment is here, and we've got a power supply which provides power to the cell, and we measure the potential across the cell, which goes to a multimeter, and the multimeter is interfaced with the computer, and we measure the stuff, or we log the system, log the data with a computer data acquisition program, is what I'm trying to say. The power flows out through a shunt of known resistance, so we can keep track of the current at all times. Also, we have a secondary ammeter here. Now, inside of the Seebeck envelope calorimeter, we have a cement sleeve that we've built, and it's thermally conductive but electrically non-conductive. And what we've done is we've put 6 thermocouples in the cement sleeve so we can measure the temperature directly at the cell. Now, the Seebeck envelope calorimeter is a box with several walls. Ours measures 12.5 centimeters by 12.5 centimeters by 12.5 centimeters. And every 2.5 square centimeters are 100 differential thermocouples. Now the differential thermocouples measure the heat flux between the inner cavity and the water jacket of the SEC. If the inner cavity is the same temperature as the water jacket, there's no signal, no flux. If the inner cavity has a higher temperature than the water jacket, then you get a positive signal out. Now, one of the nice things about this, though, first I'm going to show you a picture of the setup. This blue box here is the SEC, the seaback envelope calorimeter. This is our water cooler / heater. Power supply. This is where we collect our leads for measurements. Interfaces to the multimeter, like I said, and into the computer where we log it. Now, the nice thing about the seaback envelope calorimeter is it's fairly linear. Shown here represents 19 control data points. The dark areas, there's actually 3 of them, one's buried under here. The dark areas are platinum control cell, where we had a platinum cathode and a platinum anode. And we have 16 resistive control cells, resistors that were immersed in water. The line represents the fit. The fit is pretty good, and it's very close to 1. The results here are that, based on the best fit, the results are that the power output is equal to 0.216 watts per millivolt times the box output in millivolts, and we have this offset of 0.029 watts. Now we need that offset because we have several wires. We have about a dozen or so wires feeding through the calorimeter. Now heat will leave via the wires, and that would be a loss of heat. So this acts as an offset for that. Now we can go on to the results. Now this slide represents the excess heat as a function of reduction in thickness by cold rolling. At 0% cold rolling, well, first, here are the error measurements. The errors actually varied from one experiment to another, but these are the highest that we've encountered, so this is what we're reporting. At 0% cold rolling, we had 3 out of 8 cells give us excess heat. I'm defining excess heat as 100 milliwatts, this line, just to make things easy. If you start to reduce the thickness of the cathode by cold rolling, you see that the 8 cell experiments gave 2 great excess heat results. As you increase the cold rolling, the excess heat decreased. Now, we concentrated on this area because it looked interesting with the SEC, and we found that 8 out of 10 experimental cells showed excess heat. Now, to put a face on this, during an 8-cell experiment, you can see that the diamonds are the control cell and the line is the experimental cell. The power input to both of these were approximately the same. In fact, they were almost identical. However, the temperature output is very much different. The control cell is the bottom down here, and it's 6 degrees different from the experimental, where the power input was the same. Another way of looking at this is enthalpy released during the experiment. This is based on an SEC experiment. Now, the enthalpy released during the formation of titanium deuteride for this cathode mass here is about 627 joules. I say about, I read it up. If you take the total enthalpy released during the entire experiment, we find 179,000 joules. It's several orders of magnitude greater than the formation of titanium deuteride, which is the only thing you would expect to be giving off enthalpy in a cell. So that's a pretty large discrepancy there. So there's got to be something going on. Next, I'm going to show a pre and post characterization of one of our experimental SEC cathodes. And the purity of this material was 99.99% pure. The spectra I took with an EDS, Energy Dispersive Spectrometer. I took here and here. This is before and after. Before, we had 100% titanium. Afterwards, we had 100% titanium and a trace of sulfur. Now, the trace, the peak is very small, but the quantitative analysis is below the error level of the EDS, so it's actually below 1%. So we just say trace. The next thing we're going to do is focus in on right this area right here and this area right here. Now a lot of work was done on these cathodes, but obviously I'm not going to be able to go through all of it here, so I'm just going to show you two interesting places. Here's the first one. In this region right here, S11, you see that there's a trace of silicon. We have 1% of sulfur, 4% chromium, and 3% iron, and the rest is titanium. Down here, we find 100% titanium, which is what you would expect. Over here, we have 1% silicon, 2% sulfur, 36% chromium, and we have 2% iron and a trace of copper, and the remaining is titanium. Now, this chromium, during previous experiments, was corroborated by neutron activation analysis done by Reed College Nuclear Reactor Facility. And they found that there was chromium on excess heat producing cells, but no chromium on non-excess heat producing cells. And the cells that we had analyzed were identical. There were a pair of cells from the 8-cell experiment. Here's another area of the same cathode after the experiment. S14 shows 100% titanium. If we go over to S15, there's a trace of iron, 1% of chromium, and the remaining is titanium. S16, we find 1% of sulfur, 1% of iron, 10% chromium, and titanium, of course. S17 shows us 9% chromium and 2% iron. The important thing that I'm trying to point out here is that there's quite a bit more chromium than there is iron, consistently, not just with this cathode, but throughout most of our cathodes that we find excess heat on. Now, one may argue that this is deposition from somewhere inside the cell during the experiment. And what I'm going to show here, these two pieces of metal, this is a little dark, but these two pieces of metal are cross-sections of cathodes that were the exact same thickness. They were both 20% cold rolled from 0.5 millimeters to 0.4 millimeters thickness. And what you see is that over the lifetime of the experiment, the electrolyzed cathode eroded, it lost thickness. In fact, this one lost 43% of its thickness. This one has not been electrolyzed at all. The rate of this erosion is about 3 angstroms per second, as it turns out. Now, this erosion is pretty typical for the cathodes that we have. Another thing is that if there was deposition, one would expect platinum. That's the most abundant impurity inside of the cell. We don't find any. It's been very rare. I think maybe once out of 35 cathodes or so. We performed a Boltzmann equation calculation and found that diffusion from the lattice to the surface would occur at the rate of about 1 × 10⁻12 millimeters. And what you would expect, or what you would need to have to get from the center to the surface is 1 × 10⁻1 millimeters. So there's an argument there that it's not, what we're finding is not diffusion of impurities. And in addition, it was 99.99% pure, and there is no chromium in the certificate of analysis for this batch of titanium. Here, this is not very visible due to the slide, but there are 3 little dots. This is going to be the last picture I show. 3 little dots after the experiment. This is no excess heat on this cell. There are 3 little dots here that were not here before. I'm going to show you an enlarged view of that. And I thought I'd end with this, or end the pictures with this. Here we took a spectrum, and there was a 3% chromium, 5% iron, and a trace of nickel, and the remaining is titanium. Whereas if you go next door, it's 100% titanium. But the interesting thing with this picture is not in the elements themselves, but are these pits or are they bumps? It really depends on how you look at it. Now, this kind of gives you an idea of the difficulty of good characterization of a cathode. And you really have to stand on your head to get this right, and there's a lot of subtleties involved. Finding these regions is very difficult because they are few and far between. And that goes for both a excess heat producing and non-excess heat producing cell. To summarize, a 20% reduction in thickness gave the largest excess heat and reproducibility results with 8 out of 10 cells showing excess heat. Mechanical treatment of the cathode appears to be an important variable in the excess heat effect, and new and unexpected elements have been found on several of the excess heat producing cells. And to conclude, there may exist an optimum amount of cold work which yields the largest excess heat and reproducibility results. The excess heat generated is several orders of magnitude greater than the formation of titanium deuterite, as we've shown. The deposition of impurities on the cathode is unlikely due to erosion of the cathodes. It's very hard to deposit when you're losing an atomic layer a second. The diffusion of the impurities to the surface is also unlikely due to the low diffusion rates at room temperature. And lastly, the energy produced and new elements found are due to some other new process, such as low energy nuclear fusion. And lastly, I would like to thank Portland State University of Oregon in the United States, the Academy of Applied Sciences, the Drexler Foundation, New York Community Trust, and the U.S. Army Department of Research.
Have there been other excess heat results in big water electrolysis of titanium? You're aware of?
Yes, I believe there was. I believe Dr. Sanchez had some excess heat.
They use that
results.
too.
And I think there were several others, names escaping me right at this moment. I have a full of.
You've heard about Ed Storms, talk to Ed Storms.
Any more questions? Please, yes.
Use the microphone.
If you have a small amount of chromium sample, could it migrate into a little area, surface migration, to give you a sample of kind of a high level thing? I mean, just ask that question.
You mean if the chromium is already present before the
It's already
experiment?
present, maybe if there's a small amount and you're eroding other stuff away, could it tend to move it to one little area? I just wondered.
Well, it's possible. However, like I said, 99.99% purity, and also the certificate of analysis only shows calcium and a few other trace impurities that the company reported to us.
There is a tendency, though, for prolonged electrolysis to bring chemical impurities to the surface, I understand. Usually rhodium, for example, typically a small percentage in there, and it's much higher on the surface after prolonged electrolysis than the bulk sample gave. I know that occurs.
Well, if the chromium was in there, I suppose that could happen, but it's got to be in there first. It's got to be somewhere in the cell.
I have a question. You mentioned that the air temperature had a variation during the daytime and day and night. How long did your experiment last?
These experiments lasted from 10 hours to several hundred. I think our longest lasting experiment was 11,173 minutes. So they don't last an extremely long time, but they're not short-lived either, typically.
Cold rolling is normally done using steel rollers. Chromium steel is a very common material to use. Can you be sure that you're not picking up the chromium and the iron from the rolling operation itself? In addition, if you have not analyzed this material yourself, I would not trust the manufacturer to give you the correct answer. And one other comment, I also have a seabed calorimeter, and the heat going in and out through the wires is a problem, and that is sensitive to changes in room temperature. do you keep the room temperature suitably constant so that that is a constant source of heat or loss?
The first question you had was the chromium. If we were picking up chromium from the rollers, one would expect that there would be more iron in the stainless steel than chromium. However, I'm showing here 36% of chromium and very small amounts of iron. So you wouldn't expect that kind of disparity. I would think that you would see more iron than chromium, and that's what I was showing. And the second one, from the picture that I showed you here, this is just a setup. We've moved that into a separate room, and we have tried to, we do as much as we can, but we don't have a temperature control room or anything like that. But it's steady state, just try to do your best.
Last question, yeah.
I remember the former experiment with the palladium in your laboratory. You observed the nuclear products and explained it by the neutron related reaction. Did you analyze the present data by such a model?
You mean this
Oh,
cathode
yes,
that I showed
yes.
here? No, not this specific one, the previous ones that we've run.
Thanks to our speaker again. Our chairman has one announcement.
Just I wanted to remember the orders of posters scheduled for this afternoon, that we have at 4 o'clock a session of presentation of posters in this room. Since thus by then the posters should be set. So in this time between now and 4 o'clock, please set your posters in the first floor on the PIS where there are poster tables. Thank you.
Thank you all for the morning session.
Значит, about Earth discovery, such as means in the title, and Earth's role in cold fusion and in nature, you may read in my abstract or report. And now, these 3 minutes, I will, which I have, I shall try to show you the chronological way of this discovery, 20 years of this discovery. The beginning of this discovery, was in 1980, where the hypothesis of these particles was proposed to explain the cosmic cosmic muon momentum spectrum anomaly. The authors of this hypothesis you may show in this this transparency. It was published in Central Journal of USSR, Известия Академии наук. After this hypothesis must explain the anomaly of some characteristics of in cosmic rays. And from this time we began direct search of these particles in cosmic rays. And we have many installations was made, and only, but Azion was not discovered, this period and only after the discovery of cold fusion we can 1 minute.
30 seconds.
We can construct the theory of these particles and by Vereshkov and after 10 next years this particle was found last year.
Thank you very much. Sure. Excellent. That was a good training. Thank you very much. The next paper will be presented by Tolbert Sinchak.
I'm going to be talking about deuteron fluxing and the ion band state theory. We had a major meeting in the American Chemical Society, of which a number of people made very strong statements of the importance of deuteron fluxing. Kubri's statement that it's not an equilibrium phenomenon, it's generation of heat. Bob Bush said, where is the deuteron wind when we talked about the ion band state theory? And I think fluxing is implicit in Arata and Zahn's emphasis on spillover deuterium. The ion band state theory says that its conclusion basically is that you need a coherent partition state of matter, unlike atoms and nuclei. You have to have a partition overlapping quanta of nuclear matter coupled to a dissipated medium. Otherwise, you will get high energy radiation like you do in muon catalyzed fusion. Now, why should fluxing play any role in the ion band state theory? Well, the real problem is the experimenters have the problem of getting deuterons into a many-body state. And it may well be that fluxing provides the best way, or maybe the only way of doing such. When you have deuteron hopping to non-adjacent sites, which you have when you have most of your sites filled already with deuterons, you're really getting something that begins to resemble block function particle transport. And the point is, fluxing wave-like deuterons mimic the electron current in metals. And scattering of wave-like fluxing deuterons by inhomogeneities mimics the scattering of electrons that creates the resistance in electrical current systems in metals. Well, the point is, scattering of wave-like fluxing deuterons at a crystallite surface interface, where you have microcrystals in maybe a less ordered metal matrix, changes the distribution function which describes the fluxing deuterons. Many-body system is a system where, as a function of position, you have a population of energy states distinguished by different momentum values. And some of this fluxing population can be scattered into trapped wave-like populations, N of K within a crystallite, and this, very possibly, this N of K may be responsible for the heat after death effect. Plus, playing a role in the normal heat emission. Did I make it?
Thank you for sparing us those peeps. The next paper will be presented by Dr. Fisher.
There's strong evidence for excess power, a new form of nuclear power, in a number of electrochemical experiments. I believe this evidence, and I accept that excess power is nuclear power. By contrast, evidence for the underlying nuclear reactions is weak. Some people believe that these reactions involve deuterium fusion. This in spite of a lack of deuterium fusion ashes, practically no neutrons, practically no tritium. These people hope to find a new fusion channel involving crystal lattice interactions. It produces only helium-4 and energy, and we'll be hearing from them this week. Other people believe that deuterium fusion is not the answer. They, as do I, hope to find other nuclear reactions that could be responsible. Some people envision reactions at hotspots, at crystal lattice imperfections. Some allow endothermic reactions, provided that companion exothermic reactions repay the energy debt. And we'll be hearing from them this week also. But most nuclear physicists reject these attempts at explanation on the grounds of physical implausibility in the light of well-established physical principles. And I have to say that I too do not like them on the same grounds. My poster presentation offers a different explanation based on polyneutron chain reactions. A polyneutron is very similar to an ordinary atomic nucleus, except this doesn't have any protons. It's just a little bundle of neutrons. Polyneutrons are old stuff, or at least the idea of polyneutrons are old stuff to nuclear physicists. But not having been able to produce any, these physicists could not experiment with them. But cold fusion people can. My posters show where polyneutrons come from, how they make excess energy. I invite you to come and learn about them, what a polyneutron chain reaction does, and how excess power can be understood in terms of the mainstream of nuclear physics.
Thank you for a very nice presentation. I'll give Russ George one chance to come forward. Since I haven't seen him, I expect he's not here, and therefore his poster will not be presented. The next paper is presented by Dr. Hanawa. I'm sorry, I'm skipping people who are obviously not here. If anybody feels offended by that, please come forward.
In early 1960s, Japanese authors found out quite a lot of ion production from the carbon arc, who observed this phenomenon by using permanent magnet. Since then, it's very interesting, but only a few studies have been done up to now. So I started the experimental, more careful study and began using highest quality water. The resistivity is just over 18 centimeter, and high spectroscopic pure carbon rod was used. And also AC and DC arc was applied, but no difference was observed at all. And fortunately, one occasion, I found out that many metals are produced on the anode surface, not in the plasma or cathode. No such element was observed. So, and now I'm now constructing calorimeter to measure how much heat was produced. But unfortunately, I couldn't report here the results. But recently, I will publish it. So thank you very much.
Thank you very much. The next mini presentation will be given by Professor Kozima.
My presentation today is the number 44. The cold fusion phenomenon and the physics of neutrons in science. After the discovery of the neutron in 1932, there are very many works on the neutrons in vacuum and in solid. But in my opinion, there are lacking of one important factor neutron shows in solid, that is the neutron band. This is a simple potential model, Kronig-Penny model, very popular in the solid-state physics for electrons. And I made similar calculation for electron, for neutrons, and obtained this type of band structure of neutron energy. The difference of left and right figure is the difference of the lattice constant. So the difference of the lattice constant makes the position of the allowed band shift. Because of this shift in the boundary region, there appears this type of local coherence, I call it. The density of neutrons becomes very high in the boundary region. And as Dr. J.C. Fisher presented an idea of polyneutron to explain cold fusion phenomenon, I propose another possibility of neutron drops formed in the boundary region due to this type of very high density of neutrons. And in the case of Fisher's polyneutron, perhaps it is possible to write aggregation of neutrons. But I'd rather propose this type of neutron drops composed of few protons and many neutrons. And this is a possible agent to realize cold fusion in the boundary region. Thank you.
Thank you very much. Next on the program is Mitchell Schwartz. I know Mitch is not here and his poster is not here, so that one will not be presented. Following that is Wang.
Following the work done by Professor Takashi and Kasagi, I would like to I have done some things with the beam-solid interaction, especially on the titanium deuterates. And we use the proton to bombard the target. We found some charged particle here, and also here. And after we found it, we think it may be something anomalous. Then we use the telescope system to measure the two-dimensional structure. Here we can observe a line. This is with two charges. That means alpha particle of helium-3. And here is DD proton. So many charged particle productions. Then we make three-dimensional measurement. We can observe the peak. Here is a very strong peak. When we enlarge it, we can observe this one is proton, DD proton. And there are some small peaks here. Then we should decide whether that is helium-3 or alpha particular, we use absorption methods. Finally, we decide all the products located on the helium-4 alpha particular. Then we find some alpha particular with different energy. And we check the background. We have used a different target. And when we use this target, we can observe only limited numbers of the particular, alpha particular. And here we bombard titanium, we observe very few counts. And then we change the target. We use this target. We observe also not very much. And here we use the stainless steel, and we observe also not very much. But when we bombard the titanium deuterates, we observed a lot of charged particles. And this kind of result may be interesting for the cold fusion research. Then I gave the presentation here, and you're welcome to my post. Thank you.
Thank you very much. The next presentation will be given by Eppley. Apparently not. The following presentation is authored by Professor Samsonenko and will be presented by Professor Igor Goryachov.
Dear friends, my own report is going to take place only tomorrow. Today I am requested to deliver you an abstract of the report composed by the people shown on the screen. Briefly, gamma radiation and neutron emission under the different conditions simulating the transformation in palladium-deuterium crystalline system were examined. In the experiments, the process of the multiple recycles of alpha-beta transition, the primary recrystallization at the temperature of 300 to 500 degrees centigrade, and the accumulative recrystallization at temperature of 500 to 800 degrees centigrade were studied. The neutron emission from the palladium sample was detected during the accumulative recrystallization. No gamma radiation from palladium-deuterium system was discovered in all the experiments. As an example of the results of things, just let me show you the picture shown on the screen that demonstrates neutron emission measurements in 4 experiments with the intervals of 2 to 4 days. Points, zeros in the picture correspond to the beginning of sample heating. Pictures A, B, C, D correspond respectively to different values in initial saturation equal to 26% deuterium, 8.6% of deuterium, 8.4%, and 9.6%. Thank you.
Again, I'm happy because I'm the good guy here, but prove that you're as good as the bad guy. Anyway, now it's the turn of Professor Takahashi. His 3 minutes talk.
This is just by the collaboration of 3 people, myself and my student, Mr. Oda and Dr. Mizuno of Hokkaido University. We are going to show why we can have radiation-less fission-like products, which have been claimed by many researchers also in this conference, and why we can have non-natural, say, isotopic ratios in this kind of products. Our model is not the usual particle absorption and fission or fusion, something like that. But our model is multi-photon absorption and collective deformation will make a special fission. We call it a selective channel fission. we have analyzed many possible fission channels having a positive Q value based on the liquid drop model, and we made easiest possible fission channel and making a slice for the possible E1 resonance region by photon. And we got this kind of answer for the palladium photofission. And this is the top 10 channels opening first, and we can see easily titanium and chromium coming first, then followed by iron and calcium and so on. And I just showed you some example of mass distribution of this model compared with the experiment by Mizuno. We see considerable agreement. Also have a little bit radiation, but not much. And this is the element distribution compared also with the Mizuno's experiment. We can see very, I think, nice agreement. And also, this shows the isotopic ratio predicted by model. This also shows the drastic change from natural isotopic ratio so far. I think this kind of hot fission model will have something to do with to explain this kind of things. Thank you.
Our next speaker is Dr. Savatimova.
I would like to pay your attention. I would like to pay your attention to problem reproducibility. First, structure change это тот materials during deuterium irradiation, such as void, net of dislocation, cluster defects lead to instability in condition for nuclear reaction. In the result,